Thanks for joining us for the first seminar in this series for this year. Very exciting speakers are going to be here, but I'm privileged to start with Sylvia Herbert, who's joining us from UCSD. Sylvia started as an assistant professor in mechanical and aerospace engineering in 2021. She runs a Safe Autonomous Systems Lab within the Contextual Robotics Institute. Previously, she was a PhD student with Professor Claire Tomlin at UC Berkeley. She is the recipient of the ONR Young Investigator Award, NSF GRFP, a UC Berkeley Outstanding Graduate Student Instructor Award, and the UC Berkeley Dmitry Angelakos Memorial Achievement Award for Altruism. And today she'll tell us about reachability with the barrier function. So please all join me in welcoming Sylvia.
Thank you so much. My talk today is going to be kind of mathy, and it's a type of math that often people don't get a lot of experience in robotics. So please feel comfortable speaking up and asking the question if it's something that you're not used to. Hello. So today I want to talk about safe control from value functions. So value functions are something that have become really popular recently when we're trying to deal with safety and keeping robots safe. The concept is very simple. It's you have some function where it's positive when you're safe, it's not positive when you're not safe, and the gradients of the function tell you how to maintain safety. So we take the desired safety constraints, stay within this circle, for example, the long-term effects of the dynamics, how you incorporate in the fact that you may have momentum and acceleration, and turn that into this single scalar function. The scalar function takes in the current state of your system and outputs a level that's the measure of the safety. So the higher the level, the more positive, the safer you are. As you approach zero, that means that you're getting less safe.
So just to be clear, is safety a measurement for the robot itself or for like the surrounding environment?
Either. It depends on how you define the state space of the system. Good question. So it might be, so to elaborate, you might have some state constraints that say, it's unsafe to tilt this particular way or get your robot into a certain type of configuration. There's also safety that's like, don't hit obstacles. It can also go beyond robotics. There's one of the most beautiful applications of this, I think, is in applying anesthesia to patients, where you say failure is death or waking up during surgery. And so you want to stay within the safe region where you are applying just the right anesthesia, where you will maintain being able to remain within the region between death and waking up, as an example. Okay, so the level tells you the measure of safety, and the gradient tells you the safe or unsafe direction. So if you're trying to increase safety here, you're simply doing gradient ascent towards safer levels. It's been really useful, applied in many, many different contexts, is growing in popularity. Here are just a few of the projects that I worked on in which we've used these types of value function-based approaches to maintain safety for our system. So typically you have some performance control, you're trying to reach a goal, and then this overrides the performance control as needed to maintain the safety of your system. In fact, the new dean of engineering here is one of the big proponents of this type of approach using safety value functions. The one that I use historically is called Hamilton-Jacobi reachability analysis and Hamilton-Jacobi reachability-based value functions, and we'll go into what that means in a minute. Another one that's getting a lot of popularity these days are called control barrier functions. They're kind of a similar concept to Lyapunov functions, if you're familiar with those, but instead of trying to reach and stabilize to a point, you're kind of flipping that around and trying to stay away from an unsafe region. The dean here is the proponent of the latter approach. So when I was interviewing for faculty positions, I was often getting asked the question, okay, you're coming from this one background that's just safety value functions. How does it compare to this other background that's safety value functions? And I'd kind of mumble some response. And then once I became a professor, I was asked to teach a special topics course on safety for autonomous systems and figured that I should actually discover what the relationship is between these two things. And that's led to some really fun research directions that I'm going to talk about today. So we're going to go through the background of those two things, And then I'm going to talk about how I am working towards applying this to this pipeline that I'm excited about. So this is based on my ONR kit that was just mentioned, where I'd like to take in some initial knowledge and assumptions about my system and the environment, use that to generate a high-dimensional approximate safe value function, apply some of our tools in order to refine that approximate safe value function to make it a rigorously safe value function, and then update our knowledge online as we discover that the world is different from what we expected, and repeat. We'll go in more detail what that means, but let's begin with the background. Okay, this is where we start diving into the math. All right, so let's talk about first how we create this safe value function and then how we use it online. So to create the safe value function using Hamilton-Jacobi reachability analysis, we assume that we have a model of the system. We assume that we know the state space of the system. I have them as Z here. I think in the later methods as X. But you have states, you have some control input, and you potentially have some disturbances. This might be an actual player who's working against you, or it might be something like you have uncertainty in certain aspects of your model, and so since you're trying to do safety, you want to ask, how can I achieve my goal, even if the uncertainty is the worst case that it could be? So you treat it as if it were a disturbance. And then typically, you also have some failure region. So we talked about whether that's death in the anesthesia case or whether that's crashing into a tree in the robotic case. And therefore, you have some constraint set. You want to stay within some set where you know you have not crashed into a tree. And from this, we want to build that safe value function. So the way we do this is first we lift this to a higher level and we define a reward function over this. So in this case, the reward is simply positive reward when you are safe and negative reward when you are not. In some cases, this is sufficient for being a safe value function. You see it's positive when you're inside the constraint set and negative when you're outside. However, if you have momentum, if you have some acceleration, if you can't instantaneously stop, then if you're very, very quickly riding yourself towards the failure region and you realize that you're approaching zero and you try to brake, you may have so much momentum that you end up crashing anyway. So we have to incorporate the dynamics of our system into this function itself. Feel free to ask questions if things don't make sense. So we want to generate a value function, and the value function we want to create says I want to take the cost of my trajectory. So here my cost is this L term, and I want to look at the cost of these trajectories starting from an initial state, sorry, I messed up the math here, initial state X in this case, and an initial time. I'm going to put in my trajectory notation there. Just think of it as the squiggly line. I know that it's kind of complicated, but it's just saying this will output the state that I get if I start at initial state X, initial time T, apply a control signal and apply a disturbance signal, have the trajectory go on until time tau, it will output the state I get to there. So it's our way of shoving a bunch of information into a very short amount of space. Okay, cost of trajectory starting from the initial state and initial time. But we want one more thing. We don't necessarily want to try to enumerate literally every possible trajectory of the system. It's sufficient to ask, what about looking at just the optimal trajectory starting from an initial state and time? So if I am doing my best and the disturbance is doing its worst, will I be able to avoid that tree? If so, then just apply your best case control policy or optimal control, and you will be able to maintain safety. If not, if you, even despite doing your best effort, will end up crashing into that tree, then mark that as unsafe. So therefore, we're going to take each state and time, and we're going to do this max over U. The control's trying to do ascent towards safer regions, and min over D. You assume that the disturbance is trying to drive you into areas that are unsafe. So that's the value function that we want to find. Because we have this max-min formulation, it may not be easily solved, it may not be convex. And so the kind of standard way that we use that's very general is to do brute force dynamic programming. So if you're familiar with Bellman backup coming from the machine learning community, or if you're familiar with dynamic programming coming from the control theory community, we are essentially going to grid up the state space and look at every single point in this grid and ask how this value function evolves over time. So essentially you can think of it as starting at the constraint set and asking in one step, what are the set of states that will enter the constraint set. Okay, now in 2 steps, what are the set of states that will enter that? 3 steps, et cetera, et cetera. So it's a recursive way of solving this. The update equation that we use is based on the Bellman equation, but now we have to deal with continuous time, continuous space, and disturbances. And so what it ends up looking like is something like this. If I take a particular point in the state space, I fix x, and I look at how the value is going to change in time, backwards in time, as I reason about trajectories starting in the past. So fixing x, looking at dv dt, backwards in time. The way this value is going to evolve is based on this, which is called the Hamiltonian, which essentially says I'm going to take the spatial gradients of my function. I'm going to try to align my dynamics, dx dt, along the direction of the spatial gradients that will either drive me to go up the function or, in the disturbance case, down. So it's essentially doing gradient ascent for the control, such that it's constrained to have to obey its system dynamics. So when you're in a car, you're trying to get somewhere, you can't necessarily just move to the right without having to turn your wheel and move around. So even if the gradient's telling me to go this way, my dynamics in a car forces me to instead take a maneuver that's a little bit more indirect, right? So.
Why does the derivative operator and the maximum operator, why do they commute?
I'm sorry, I can't quite hear you.
Why do the derivative operator and the maximum operator commute?
That's a good question. I don't know if we have enough time to go through it right now, but I'd be happy to talk more offline about how we structure this. Okay, so this is how I want to update my system. Note that the dx dt right here, x dot, is simply my dynamics of my system. So I can just plug in f of x, u, and d right there. All right, so I'm going to take this initial reward function, grid up my space, and apply dynamic programming backwards in time using this update equation everywhere. And in this case, this is what it looks like. I'm going to run it for, I think I did 1 second. Okay, this is now my value function. This is the function that tells me when I'm positive, I will be in the constraint set, and when I'm negative, I will not. That means that if I take the 0 level set, slice it there, and flip it around, these are the set of states that will be in my constraint set in exactly 1 second. And that's because I set this up as a terminal reward problem, where all I care about in this situation is reaching my constraint set in exactly 1 second. You might point out that some of this is outside of my constraint set. So I'm saying, if I've already killed someone, don't worry, there's a path for me to get them back towards, the safe level anesthesia over time. Often in safety problems, that's not good. We want to stay outside of the constraint set for the entire time horizon, right? So let's modify what we want from our value function and modify the update equation accordingly. In order to say I want to stay within the constraint set the entire time, what I'm essentially saying is I want to keep track. Oh, this is just me asking this. What if we care about the states from which we can be in the constraint set for the entire time horizon, in this case 1 second, instead of just at the end of the time horizon? To do that, we're going to add in another minimization term here, where now I'm putting in a minimization over time. That means I want to keep track of the minimum cost of my trajectories over time. If I have a trajectory that started safe, but then reached negative reward, and ended up in the failure region, that is not safe. So I only want to keep track of all trajectories for which the minimum reward they achieve must remain positive, must remain in the safe set. So now I want to add in this minimum over time to my update equation. The way we do that is a little bit non-intuitive, and I don't have time to get into all the details here, but I'll tell you high level. First, let me just move the left-hand side of the equation to the right-hand side, so nothing's changed there. I just move that over on the other side of the equation. And now I'm going to add in a minimization term. So I have now min between this top thing and my original update equation. That is essentially saying minimize with my reward function at each point in the update. What it does in practice is, I'll show you here. Oh, and this is now a variational inequality, not just a PDE. It looks something like this. So you see it can never grow beyond the original reward function. I'm only keeping track of states that remain within the constraint set at all times. This is my new value function, positive safe, negatives unsafe. Where here, if I take the 0 slice, this now corresponds to the states that will be in the constraint set for the entire time horizon, in this case 1 second. So there are some states here that if I start in this state, I will be forced out of the constraint set and into the failure set, despite my best case effort of remaining inside. Whereas the states here, there exists some control so that I can remain safely within my original safe constraint set. Questions on this so far?
So in all of this, you're identifying the safe initial conditions through this process?
All of this, I assume that I am given the constraint set. So I'm given what is considered a failure within the state
you
space.
have the constraint set, but in the output of this process is the control that, and then that region that you're highlighting is the like safe initial conditions.
Yes, exactly. Yes. So these are the set of states that I can start from safely. And we'll get into this in a second, you're ahead of me, and there exists a control policy that I can get out of this that will keep me safe. Often, we're interested in safety not just for a second, we're interested in keep remaining safe for all time. You know, you want to make sure that you never run into that tree on the highway. And so you'd like to come up with the infinite horizon safe set. For that, we can, again, I asked the question here. Okay, what if we care about the states from which we can be in the current state set forever instead of for a fixed time horizon? That case, kind of what we do right now is simply just keep running this until it looks like it's converged. So just keep going, see when it stops propagating. It'd be great to have some theoretical properties on knowing that it will converge. In practice, we rarely do. But in this case, it happens. So eventually, around 4.5 seconds, it stops updating. That means if I were to keep updating this for infinite time, nothing would change. So it means that this is the safe set that can be applied for an infinite time horizon. If I take the 0 level set now, which looks kind of similar, these are the states that will be in the constraint set for all time. In other words, this is a control invariant set. You've heard of this. So if I start inside of this green set, I'm guaranteed to stay not only within actually the constraint set, but I'm guaranteed to remain within the green set. It is a control invariant set. So often with safety, we care about this type of thing. Find the set of states from which, as long as you stay outside of that set, you know you can apply whatever other performance-based controller you want, you will stay safe. Okay, now let's discuss how we get the online control from this. We've just constructed this offline value function. How do we actually use this? So looking at this update equation, it's actually a very similar thing that we use for the online part. I'm going to take that bottom part, the PDE thing, and the online control is actually simply looking at the gradients in my value function, aligning them again using an inner product with my dynamics, and trying to do gradient ascent along that. So if I have my, and if it's infinite horizon, it's not even a time varying value function. It's just one function, depends only on state. I look at where I am right now in the state space. I look at the gradients of the function, and the gradients of the function tell me the direction I need to move in order to maintain safety, and are designed in such a way that if I align my dynamics along them, I'm guaranteed to be able to remain safe. And so these incorporate in the dynamics of the system. They understand the fact that if you are accelerating near the boundary of the failure region, you will not be safe. And they find the region for which, as you try to turn, as you try to decelerate, the set of states for which you can remain safe. So this tells me whether I'm safe or not, whether the value function is positive or negative, where the boundary is, where the 0 level set, and the optimal safe control to apply to try to run away from the failure region. Any questions so far? Okay. That that's what we do for reachability. It's a very nice online, because for control and disturbance affine systems, which robotics it often is the case, this is a simple linear program. You can solve it analytically very, very fast, and it's easy to do. We'll talk about some caveats of that in a second.
So in here you have like a bounded disturbance something.
Yes, so we assume that we have bounded control and bounded disturbance, and we're doing a worst case analysis over this disturbance. So you can think of all sorts of implications of what that means if you assume that, for example, you always have hurricane conditions when trying to drive home kind of situation. Or if instead you do the opposite and you assume that the world is great and your bounds are really, really optimistic. And so that key part of the loop that I talked about of like finding out what is actually going on in the world and updating your information is pretty crucial when you're trying to think about worst case safety analysis, figuring out what is worst case.
And like, do you have any existence conditions that we're going to discuss later? Like, you can imagine if there's a bounded control and bounded disturbance, you may not have.
Yes, so like I said, the convergence thing, we don't have very good theoretical properties on when this will converge. If you have, let's say, infinite disturbance and a small control, then eventually your safe set will vanish depending on the structure of your system. Usually then you have at least a finite time safety thing that you can say. So at least for 3 seconds, I can stay safe before the disturbance totally wipes me out. And so you might be able to say something in that case. But the infinite horizon solution, getting a control invariant set, is not always true. It might, if the wind can literally pick me up and put me anywhere at once, then there are no guarantees on me being able to get home. And so if there exists none, we will not recover a control invariant set there. If there does exist one, this will recover because we are doing brute force dynamic programming. So it's very generalizable in that sense. We can make really nice theoretical guarantees. The issue is that we're doing brute force dynamic programming, which we'll talk about. Okay. I want to briefly talk about properties of this online control policy. So that was that update equation that we looked at from before. If I look at just the PDE part of it, the min between the PDE and this other term is equal to 0. That means the output of this must be greater than or equal to 0 if the min between that and something else is 0. So pulling that down, looking at this is how my value function changes directly with respect to time. And then this is how my value function changes indirectly with time. So how it changes with respect to x, and then x dot, how x changes with respect to time. And so if I apply this using and plug in my optimal control policy, this will actually give me v dot, my total derivative under the optimal control policy. So this is saying that the change of my system over time, as it follows this value function, is going to be strictly non-negative. So the change in my value over time with my trajectory will only reach safer and safer levels. I'll never decrease my level of safety. If I'm at safety level of 5, let's say, it will only go up and up the value function. This means that my trajectories are kind of constrained, even if I'm very safe already. If I apply this control policy directly, if I'm only always trying to do gradient ascent as much as possible, then I can only allow myself to move towards safer and safer directions away from the failure region. So this can be kind of conservative and unrealistic. So if I start with a safety level here, I can only monotonically increase my safety. Because of this, in reachability analysis, we often instead apply something called least restrictive control, which is just kind of, in a way, a hacky way of saying we're only going to apply this safe optimal policy when you get really close to the boundary. So I consider my safety level as here at 0. And if I'm above 0, if I'm safe, do whatever you want. But when you get close to the boundary, you apply the optimal safe control, run away as fast as you can, then do whatever you want. If you get close to the boundary, apply it again, run away, etc. This can be nice. It's least restrictive, so it allows you as much as possible to do whatever it is that you want to do for performance. But it can end up with pretty silly looking trajectories that have these kind of jerky maneuvers along the boundary. And so you can end up with values that kind of go up and down and up and down. Does this make sense, this trade-off here? So sometimes we do something in between. We do this like weighted averaging of kind of heuristically saying as you start to get closer to the boundary, apply the safety control more and more. But this is usually not put in the papers. It's just something that you do when you're trying to make your actual robot work in practice. Okay, so to recap, it's nice because it is it's constructive. I can make a value function, whether it's only for a finite time or whether it's for an infinite time. It's general. We can deal with a lot of just general nonlinear systems that have bounded control and disturbances. And it recovers the maximal safe set given this, because we're doing brute force dynamic programming. We can deal with bounded control and disturbances. So we can deal with the fact that you have limits on your actuators. And you can't just apply infinite acceleration at the boundary of the safe set. And there are actually many flavors beyond the infinite time safety case that I'm talking about now. We can do reaching goals while avoiding obstacles, dealing with moving goals and obstacles. Here's one example that I won't get into where I have now a goal that's in blue and an obstacle in red. And if I know exactly how that obstacle is going to move, I can actually incorporate it into the construction of my value function and end up with a value function that tells me how to reach the goal while avoiding that moving obstacle or multiple moving obstacles. These shapes don't have to be convex. They can be whatever you want within, as long as you can describe them within a gridded state space. So that's nice. You get pretty sets out of that. There's some really big disadvantages, though. One is that what we just talked about. Online deployment of the value function is not straightforward. Either it's too conservative or too jerky or something in between. We discussed that. And then the big one that is kind of called the curse of dimensionality. And this is that gridding up thing that I talked about. So if you have a 2D system, you're gridding up a square. If you have a 3D system, you're gridding up a cube. There's exponentially more points you have to compute over, 4D, 5D, et cetera. Each dimension that you add, each additional state that you add, now you're considering position, velocity, angles, acceleration, et cetera. You're adding exponentially more grid points that you have to reason over. And so this very quickly blows up to the point where it's not useful. And when you care about safety, that's important, right? So if I have a quadcopter and I need to simplify it down to like a point mass that just moves up and down, and I do a safety analysis on that, it's not really going to represent the quadcopter. If I have a human that I'm trying to stay safe with respect to, and I assume humans are just double inverted pendulums, then that's not going to capture everything that a human might do in a safety critical situation. Okay, so that's reachability. On the flip side, we have control barrier functions. Here's the definition of a control barrier function. I'm going to, and for the sake of time, just kind of summarize it quickly here. We must somehow acquire a function where the 0 super level set is safe, so everything above 0 is safe, just like we were talking about before. It must be above 0. And within that set, every state satisfies this particular inequality. It satisfies that if I try to do gradient ascent up the function, that the change in my function is going to be greater than or equal to the negative this. So I'm going to move this to the other side. This is what this looks like is if I have my function and my time, there's actually a bound on here that's an exponential curve, and my trajectories must remain above this. So this means rather than before when we had a line that came across and I had to stay above my current safety threshold, if I'm very safe, this allows me to decrease safety. It allows me to move towards the boundary of my safe set. But as I get closer and closer to the boundary, it forces its constraint more and more. And so I can move down the safe set, but I will never be able to leave it. This is a very nice property because you can put this into an online quadratic program for control affine systems, and will very naturally do this trade-off between the performance control and the safety control. So it'll naturally allow you to tune how much you can approach the safe boundary while maintaining safety guarantees. And you can actually decide how aggressively you want to maintain the safety guarantees by changing this gamma parameter that changes this curve. Any questions on that? Okay. control barrier functions. The CBF QP nicely trades off between the performance and safety controller in a very well-established, non-heuristic way. And one thing that I used to think of as a disadvantage, and sometimes is that it's not trying to find the maximal safe set. You often use simpler functions that are more conservative, but also more intuitive and easy to use. So for example, let's say I have a system that exists in velocity and position, and I have some constraint set here. Reachability might give me some interesting set that's safe that looks like this. Whereas the control barrier function community might instead of doing this funky 2D value function, but instead just define a safe set that's only in position. It's a 1D, maybe even analytic function that stays safe, doesn't recover all of the safe regions, so maybe you can't do as interesting maneuvers, but it's maybe analytic, maybe very easy to use data-driven methods to derive it, and you can store it and use it easily online. Big disadvantage is there's no general constructive method for this. There's ways in which you can, for certain types of systems, come up with this, and there's a huge explosion in people using data-driven methods to try to design these. But then when you have data-driven methods, making sure that it's actually valid everywhere, especially on that zero boundary, becomes a pretty big pain. You typically, like we just said, recover a subset of the maximal safe set, and it's usually hard to encode control bounds, disturbance bounds, these types of things. So often you assume that you can apply infinite control if you need to. Okay, so now I can actually answer the questions that I kept getting in my interviews in terms of the difference between these two. Before I move on to how we smush them together, any questions, high level on that? Okay. So this is what I envision trying to do with my students. This requires answering a few questions. The first one, the green steps, is can the theory and tools from Hamilton-Jacobi reachability, this constructive method, be used to create the best, the maximally safe control barrier functions? Can we use reachability to create a constructive method for control barrier functions? Next, the blue part. Can tools for quickly approximating control barrier functions be used to create efficient initializations for Hamilton-Jacobi reachability? So instead of doing that whole long propagation over time, if I have a good estimate designed by experts who are used to handcrafting or using data-driven methods to create control barrier functions, and they come up with an approximate solution, can I start with that and just iterate on that to get closer to the true maximally safe version? And then the third question is, can we update these functions online based on changing assumptions and knowledge of the system and the environment? So let's begin with the first one. Can we just kind of smush together the ideas from reachability and control barrier functions? The answer was yes, with a bunch of caveats that I don't have time to get into in terms of the nitty-gritty of the theory. But if we recall, the main gist of the reachability thing was we were able to start with this equation, and using this equation come up with this property, which is that we always increase safety. The big difference between that and the control barrier functions is instead the control barrier functions group has this gamma term that allows you to decrease safety as long as you remain positive. So is there a way to just kind of add that on into our computation so that we can create that constraint embedded within the value function itself when we construct it? So we just tried that. We just added a term that was this plus gamma v thing. If we went through the same exact process that we did before of doing the min between these is 0, so the right-hand side is greater than or is equal to 0, then what we end up with is v dot plus gamma v is greater than or equal to 0. So v dot is greater than or equal to this minus gamma v term. And so we can encode in the update equation, when we're actually constructing the value function, this requirement that I don't just want to always increase safety, I can allow it to decrease, but only by this certain amount. So we did this, and we played around with the theory, and for at least for finite time solutions, this works. For infinite time solutions, you can get into some hairy theoretical details, but in practice, it works super well. So we can rigorously construct a CBF-like function that encodes control and disturbance bounds. The decay rate that you want, you can actually encode, I want this particular maximal decay rate, and it guarantees online feasibility. We haven't yet, since we did this during COVID, we haven't yet done robot experiments on this, but here's an example where using the safe control only at the top, if I have some obstacle here and I start here, it's always going to run away from the obstacle. So it just runs away forever from the obstacle. If I'm doing least restrictive control instead, as I approach the boundary of the safe set, I switch between the two. And so I'm able to reach my goal, but look at the control policy, or the control signal over time. If we use the QP now generated from our CBF-like function, then again we're able to reach the goal, and our signal is much smoother. So we just recently presented this at CDC. Some next steps. We're dealing with now some of the hardcore theory stuff of dealing with infinite time solutions. Handling points of non-differentiability. If you have interesting kinks in your value function, where on one side of the obstacle you go left, on the other side you go right, you can have some weird behaviors right at that point where it's not defined whether you should turn left or right. And resolving some numerical challenges that we can have in some cases. We're also doing an extension to control the Lyapunov functions that I don't have time to get into now, but I think is really exciting. Okay, so that's the first one. Yes, we can use some theory and tools from Reachability to construct control barrier functions. It's great, we now have a constructive method. The downside is we just brought all of those issues with the curse of dimensionality and whatnot to the control barrier function community, which they may not be super grateful about. So how do we deal with that? The idea here was, well, there's all this work from the control barrier function community on trying to approximate, get as close as you can to a control barrier function that's valid. And then there's a bunch of work on trying to iterate on that to get closer and closer to a true solution. What if instead we use all that knowledge and tools to generate fast approximations, apply our reachability to it, and hopefully in future iterations, with just a little bit of tuning around key points, we can get to the true safe control barrier function. So yes, synthesizing an approximate one is easy, but you often end up with cases where they're either conservative or they are unsafe. So here's an example where we have, I think, the 60 quadcopter trying to reach this goal that's right on the boundary of the safe set. It would be safe if you make sure that you're not going too fast when you hit the goal. But the CBF here is not constructed in such a way that it actually maintains that, and instead is overly conservative. Or you can have one that ends up being unsafe. So here there's another goal, and instead the control barrier function, using that, we end up violating the safety constraints, and then again doing something that's not very performant either. So we just have a paper that was going to be in IROS, where we apply these reachability tools to an initial control barrier function, and we can show that if you start with something that's too conservative, so the safe set is way, has way more that you could recover, by applying our reachability tools, we can iteratively create less and less conservative safe sets and eventually converge to the maximal safe set. And if instead you have one that's unsafe, where you think that something is safe that is in fact not, with each iteration it becomes safer until it eventually converges to something that is guaranteed to be safe. And this is our example. So here, using the same setup, but taking that initial control barrier function and iterating on it, we're able to get this control that is both safer and has better performance. And we can do this in much fewer iterations than we did if we were to try to construct this from scratch. The algorithm and code is available in Python. Next steps here. We want to right now we're just doing something very simple of updating everywhere in the state space. But you may find that if the control barrier function is valid in most regions, or is invalid in some regions that you don't care about, it's way over here that it's invalid, it's way far away from the boundary of the safe set, can you instead just locally update in the region that you care about along that zero boundary, that's the threshold between safe and unsafe? So we're working with Professor Sean Gall in computer science at UCSD because he has this whole team working on training the control barrier functions. They can identify the regions that are invalid, and then we go in and update those regions. And I also have some previous work on trying to decompose high-dimensional systems. Perhaps we can use this in this application as well. So we take some initial knowledge and assumptions. We use the expertise from the control barrier function community to come up with an initial approximation. We then update that approximation using our tools for reachability analysis, and then we use that online to get safe control. Now, the last one, can we update these functions then based on changing assumptions and information? So we've explored this a little bit on the reachability side of things. So I have this paper from ICRA last year in which we were using tools from reachability to update reachability-based safe sets online. So here, again, unfortunately COVID, so it's in simulation, not in practice. We have this 10D quadcopter that's trying to do this figure 8. It then gets blown off course. It quickly does this reactive contraction of its safe set that I won't get into right now. But then it gathers information about the disturbance, the new disturbance, using a Gaussian process, updates its knowledge of the disturbance bounds, and updates the safe set based on this. And we have some theoretical guarantees that as it does this update, it will converge to the new valid safe set. This is really hard to do, especially in 10 dimensions using dynamic programming. So the way that we got away with this is using these 3 techniques. One was decomposition, so we took the 10-dimensional system and we decomposed it in such a way where we could analyze separate subsystems in such a way that when we then recombine it to the high-dimensional system, we can get guaranteed safe, though sometimes conservative solutions. We also do worm starting, so similar to what the previous project, rather than recomputing from scratch, if you take your previous value function, you find out that the world is different than you expected, but hopefully more or less similar. Perhaps it's only locally different. Can you start with your previous solution and iterate from there, rather than recomputing everything from scratch? It's called warm starting your computation. And then finally, we use very, very simple initial attempt at doing adaptive grids. So we first compute it on a super coarse grid. Very inaccurate. You get these hilarious looking cartoonish types of sets. But then we warm start with that cartoonish set on a refined grid. So we port it over to something that's finer and update it from there. Using that, we had, okay, so blue is the initial computation for the safe set, and purple is the update when we found out that the world was different than we expected. Using decomposition, we're able to actually solve this in general. With a 10D system doing dynamic programming, it would be like, one of my colleagues calculated it, it's like longer than the universe has existed or something to compute. But with decomposition, we can do it, in a long, many, many seconds. And then if you update it and redo everything from scratch, again, it takes a long time. If you do decomposition and the worm starting, the first computation takes the same amount, but then if you reuse that when you find out that the world is different, then we're able to reduce the computation time if it's different locally to something much smaller. If you do all of that plus this adaptive grid thing, we're able to reduce this by quite a bit. And so we're able to take something that would be intractable before and do it somewhat online to be able to update your safe sets as you learn new information. We'd like to now try to apply this to the control barrier function case rather than staying just within the reachability case. We have not done it yet. So the next step is to use adaptive tools from the CBF community with the safe learning to try to efficiently update the control barrier function in the face of new information. If anyone's familiar with backup policies and control barrier functions, we apply those and actually incorporate them into the function. And as one thing that we're excited to try out is as the fundamental knowledge of the system changes. So for example, the state dimension itself changes. Something drastically changes to the model besides just some parameter changing around. Is there a way in which we can map our previous solution onto our new estimate of what the model, the state space is, in such a way that we can try to, again, get as close to a safe solution as quickly as possible. Okay, So that's the loop that we want to try out. We started some work on that, but we still have a ways to go. I have had many, many collaborators on this who have made this all possible. There's no way in which I could do this by myself. So I want to acknowledge the people who I employed to help me when starting out with this idea. Professor Kaushal Srinath is a controlled barrier function expert, and Professor Claire Tomlin, my previous advisor, is a Hamilton-Jacobi reachability expert. Spent a lot of time finding out what are exactly the differences in assumptions and differences in tools that is used in both of these fields. The first project that we're doing where we're exploring all the theory, that's this particular core group. The second project is in collaboration with Professor Sean Gao and his students on combining this with the data-driven methods for creating control barrier functions. And then the third project is also with him on trying to update your knowledge and iterate as you are doing something online. We're hoping to eventually, Professor Henrik Christensen at UCSD has this fleet of autonomous golf carts that he wants to like run through students. And we're hoping that one day we'll get to that point. But right now we're still exploring the theory before we attempt that on campus. So if you have any comments, questions, concerns that we don't get to in the question and answers, this is my website, and then my email is very easy to remember. It's just sherbert, like the ice cream, at ucsd.edu. And with that, I am done. Thank you so much. Switch mics.
Do we have time for some questions? I'll run the mic. Any additional questions?
Just a question. I'm just trying to think about the reachability. I remember back in the day when I was working on some related problems, we were using ellipsoids, so they're very defined geometric shapes. So I just wanted to see where it stands, adapt something like ellipsoid versus brute force searches.
Yes, absolutely. So to repeat, there's been work on doing approximate reachability using ellipsoids or zonotopes, where you kind of, rather than trying to create the exact reachable set, you have some bounding ellipsoid or zonotope and you propagate that over time. And this can work really well, especially for linear systems where it's mostly scaling and rotating the system over time. For nonlinear systems, you often get into pretty bad approximations when you're using ellipsoids, but they're way faster. So one of my students is really excited about, he's caught the Coop mania, and he wants to take a low-dimensional nonlinear system that is still too high-dimensional for us to do the brute force dynamic programming to, lift it up into some higher dimensional linear approximation, and then apply some of the really fast ellipsoidal, zonotope type methods of reachability, and then try to map it back down onto the nonlinear space. He's actually, instead of doing the ellipsoidal methods, he's using a Hopf-Lax formula from Stan Osher out of UCLA, which I do not understand, but he's an applied math guy, so hopefully he does, because I'm paying him to understand it. But that's a great question. For a lot of cases, it is really useful to use ellipsoidal type stuff. So for example, there's a group out of Michigan, Ram Vasudevan and his students, that have done ellipsoidal type things with rotations. They call it rotatotopes, I think is the name they came up with, for doing reachability for a robot arm, where each joint you think about, okay, where can this component reach, where can this component reach, and then by doing each one separately, they can combine them together and get pretty fast, pretty good approximations for something that's moving slowly like a robot arm. So there's situations in which that absolutely is just good enough and the way to go, and there's situations in which it's it can have pretty bad approximations if you go to that. Other questions, comments, concerns?
Maybe I can ask one.
Oh.
So yeah, thanks. A great talk. Very inspiring. Just a very technical question. For the adaptive grid, from the picture, it looked like the grid remains uniform. And I was wondering, can you sort of focus your grid more on the boundary or something, or would that not work?
That's such a good question. Yes, we did the most simple thing that we do, like literally use the same exact function and said add more grid points into this uniform grid type thing. The right thing to do would absolutely be adaptively tuning the grid and really getting people from, for example, fluids, where they've been doing this forever, of where you have very non-interesting laminar regions of your space to not worry too much about that, where you have really turbulent, interesting dynamics happening, grade more finely, plus adding in the what you know about safety. So I care about this region of space more than I care about that region of space. And so somehow combining these together so that you can adaptively sample more densely in regions where safety is critical and where things are changing very quickly, and less densely in regions that you don't care about or where things are changing less quickly. We have all the theory for that. It's fairly well established. We just haven't yet got the student who's interested in doing the adaptive gridding type stuff yet. We're kind of doing that with the CS people because they're forced to do this with their trained control barrier functions, forced to grid up the region that they have that's invalid and only that region. But again, you have to then deal with people who like doing data structures and stuff. So if anyone wants to do that, let me know.
I have a question for control barrier functions. So let's say there's a robot and a human in the environment, and predicting humans' behavior is very hard. So can control barrier functions be used in these situations?
Yeah, very good question. Yes, great question. So if I wanted to rigorously encode this in the global state space and be 100% safe, I need to know exactly how the human is moving over time, or do a worst case assumption of a human, assuming the human might go anywhere, anytime, and you have this exploding obstacle that you're trying to avoid over time of where the human might go. It's very unrealistic. It's used a lot in the HRI space. In the relative state dynamics, so instead of thinking about the global state space, thinking of distance between me and any given human, and computing the safe set around that. And there's also work on trying to, instead of doing worst case assumptions over where the human might go, instead generating, some risk-based predictions over where the human might be. So some of my work has been on trying to establish a set that's kind of you can think of it as like a 95% confidence that the human is going to be within this region, and you treat that as your failure region and try to avoid that. One other issue that you can get into with control barrier functions, with dealing with multiple humans, is you might have, since you computed one computation of how to avoid a human, if now you have multiple humans, one computation might tell you need to turn right to avoid that human, and the other one might tell you need to turn left to avoid this human. And what you actually need to do is just go straight between them. But when you're trying to deal with the intersection of the two control policies, you might end up with something that says that it's infeasible. You end up crashing into a human, even though there was, if you considered both at the same time, a path to get through them. And so one of the projects that I have with Professor Shangao and his students is on how to try to encode some of that knowledge of how to deal with interacting humans in such a way that doesn't blow up your state space because you're considering, n number of people.
This is not a safe. Anyway, so I wanted to ask whether you are also concerned with learning policies that stay within the safe space. So if I got the talk correct, you're trying basically to compute offline the first part, computing the value function. Can agents interact and also learn the safe space as well?
Yeah, so what we're trying to do, what we're betting on right now, is that you have some initial assumptions and knowledge, and you're trying to encode that offline and do all the heavy lifting offline, so that you get something that is hopefully a prior that's close enough to what you would experience online, so that you, when you do online updates, when you do learning online, you just need to update it locally and you're close enough to the true solution that you don't need to, you know, find enough trajectories online within the entire state space to generate it from scratch. And so that's what we're currently doing as our approach. So yes, we're doing both offline and online learning in these projects with computer science with Professor Sean Gao, but we're trying to do as much of the computation offline as online. One of my students is now also getting into the hype of out of distribution stuff, and so we're starting to explore those directions of what happens when things are fundamentally different from what you expected before, but we haven't made a lot of headway on that yet.
So, can you like code it as a constraint the MDP, the whole design?
Can I include what as a constraint?
Can the problem of finding the safe space be encoded as a constraint the Markov decision process?
So there are people who look at usually for discrete states and discrete time, more MDP type approaches to trying to quantify safety. One of the really exciting ones is out of Stanford, Professor Michael Kokendorfer, who worked on the new ACAS-X for airplane, for commercial airlines, the control of that, maintaining safety there, where he set it up as a POMDP and was able to do a bunch of really cool safety analysis of that.
So the example that you gave about anesthesia, you have like two different kind of unsafe cases, right, where the either death or waking up, and I'm wondering if, because that would result in like kind of a compositional value function. I'm wondering if there's any special considerations that you can make under that. I mean, like your dynamics are still like the same system, and so I suppose that can't be decomposed at all, but I'm wondering if that's like an area of research where people consider like addressing the different cases separately or any kind of advantages.
Yeah. So one thing that's nice about reachability is we don't need to have like convex compact sets, and so we can actually have these distinct failure modes and incorporate it into one computation. A lot of the ways for generating control barrier functions require having, you know, some compact or convex set, and so they kind of are forced to, even for just two obstacles, they're forced to come up with two different solutions and then figure out how to compose them online in some clever way. And in reachability, it might be useful to similarly compose them differently if, in the obstacle case, imagine that there's multiple different configurations of where those two obstacles can be. Sometimes it's easier to just know how to handle obstacle A and obstacle B, and then online you compose them together. So yes, there's a lot of work in that area. Reachability, if you know ahead of time where those failure regions are, you can actually have this nice, beautiful, unified value function that considers both. But the short answer is yes, people do that.
I'm just trying to see connections between what you're doing
Yeah,
and
please.
what else I have seen in safety. So, you know, you're designing for worst case, right? So you're very conservative design. So how does this compare to something like a tube MPC that at least they try to be also taking some safety into account?
Yeah, so tube MPC, at least the versions that I'm familiar with, are also doing robust control, so they're also considering worst case of the uncertainties that you have. There is a big push on trying to get beyond worst case, because if you actually apply worst case solutions to like, you know, the golf cart navigating through students, it'll just be frozen the entire time. And so there's a lot of work on trying to instead use, you know, C-bar methods and whatnot that are looking at measures of risk and only considering, you know, you discount, you know, very, very rare possible events, and you try to maintain safety within some confidence region. There's also things that try to, you know, adapt very quickly. Your estimates of what the disturbances could be or the uncertainties could be. There's approaches on trying to classify, you know, human drivers as like nice, safe human drivers and like mean, aggressive human drivers, and then have different notions of, you know, safety with respect to those. But it's really, really hard. It's in general, especially with something like dealing with humans who are so unpredictable. If you try to always be safe, then the human will take advantage of you and cut you off because they know that you're going to try to be safe. If you relax that at all, then you end up potentially hitting someone. And so figuring out what whether we should do worst case, if we shouldn't, all that stuff is more on the policy side of things. The challenge with carrying like an entire distribution with you and doing dynamic programming is that now you've added even more computational complexity to something that's pretty intractable. So we rarely do you see people, except in the linear dynamics case, trying to do full-on stochastic reachability because of this. So instead we're scrambling, trying to find different methods for that. So there's a lot of work now on reasoning about risk instead of robust worst-case solutions.
Any more questions? Well, all right. Let's thank the speaker again. Thank you, Sylvia.
Thank you.